All right, our last topic for section 4 is sampling with and without replacement. So sampling with replacement is when I'm going to take something out, record what's happening with it, and put it back in. So if I was taking a sample of students in our classroom, if I were to take and select, say, Elizabeth, and then I would put her name back into the hat and potentially select her again. A little bit silly when we're actually doing sampling with people. So most of the time then we'll be seeing sampling without replacement, where if I chose Elizabeth's name, I would not put her name back in the hat and potentially ask her the same question again. So let's go ahead and see what these examples look like, because I think that's the easiest way to deal with these. So our first exercise has tires salvaged from a train wreck that are on sale. We also can see here that we have 15 tires offered for sale, and 5 have suffered internal damage, and the remaining 10 are damage-free. We're going to randomly select, which is how you know this is a sampling problem, this is what lets us know, and purchase 2 of these tires. So first question is, what type of sampling? Are we dealing with sampling with or without replacement? Am I going to just look at the tire and decide if it's damaged or not, or am I going to take and then put it back in the pile, or am I going to take it out of the pile? So hopefully you recognize that this is going to be without replacement. If I'm purchasing 2 tires, I can't purchase the same tire twice. So when I purchase 1 tire, it's basically going in my car, and then I'm taking it home. So we're going to purchase the tires, so we can't have this issue with replacement. So first thing we're going to do is we're going to revisit our tree diagrams from section 4, because basically, as you can see right here, sampling without replacement, our trials are not independent, which means our probability is going to change depending on what happened first. So this is all about those timelines we sort of saw with the tree diagrams. So we start out, and in the beginning of this whole thing, we have 15 tires, right? 1, 2, I'm just going to go ahead and draw them all. And 5 of them are bad tires. I'll make them sad face tires. And the rest are damage free. Those are good. So once I go and I purchase my 2 tires, we're going to sort of pretend that these 2 tires are purchased one and then the other. So that way we can actually see that tree diagram, the different timelines that things could happen in. So we start with all these 15 tires, and it's possible for the first tire I buy, 2 things. If I'm lucky, it's damage free, right? And if I'm not lucky, it's damaged, if I'm in the darkest timeline. So if it's damage free, well, what's the probability of that happening? And I'm not even going to use notation here because we don't need the notation. So damage free, well, this is just a strict, regular, classic probability problem. We have 10 damage free tires out of 15 tires, right? So 10 out of 15. And the probability of damage, well, there's 5 damaged tires out of the 15. Here's where things change. After we bought our first tire, we again have 2 options, damage-free or damaged, right? Except for now, we know we just bought a damage-free tire because that's what timeline we're in. So this is our new sample space, right? Instead of having all 15 tires, there are only 14 tires left for me to choose from. And of those 14 tires, 9 are damage-free. But I still have 5 damaged ones that I could end up with, right? Same thing on the other side. If you take a moment, pause the video, and try to figure out those 2 probabilities on your own. Alright, so in the second timeline, right, in the darkest timeline, we have selected a damaged tire, right, sadness. We already have a useless tire in the back of our car, and now our sample space looks like this. And so we still only have 14 options because we took away 1 tire. But now, 10 of them are damage-free and 4 are damaged. So then we have all of the different possibilities here. In this first group, we have 2 damage-free, right? We got a damage-free and then a damage-free. Second set, we have a damage-free and a damaged. Next, we have a damaged and a damage-free. And then the last or darkest timeline, we end up with 2 damaged tires. And to find these probabilities, as we did with the regular trees, we're just going to multiply these two things together. So we'll go down those rows and we will figure out what our different probabilities are. So this first one is 0.4286. Oops. We have 0.2381, another 0.2381, and oops, 0.0952. All right, and just like our regular tree diagram, all of these things, if you wanted to check your work, should sum to 1. All right, so here are the questions that we could actually be asked. So for a traditional sampling without replacement question, I'm not going to ask you to create a tree diagram. I only did this so we could really see what's happening with this problem and hopefully truly understand it before we just jump into the actual questions. So our first questions, what is the probability that both the tires will be damaged? So if we look down our tree diagram, both tires being damaged is our last option. So this is 0.0952. Now how do I do this if I don't have the tree? Now if I don't have the tree, I'm going up to the beginning where it says I'm sampling 2 things. So if I'm sampling 2 things, that means I have 2 random events that are occurring. And I sort of give myself a space for the probability for each of those events. And if they're both damaged, that means the first one is damaged and the second one is damaged. And then I just play this game for this scenario. So damaged, well, that's 5 out of 15. And then I took out that damaged tire. So now I have a 4 out of 14. That's how I usually do these instead of doing the whole tree, because we don't need every single one of these. And the question on the test will just ask for 1. Okay, next one says the probability that neither tire will be damaged. So now which thing are we caring about? Well, we're caring about them both being damage free. So again, we can see the answer to this on our tree diagram. And again, if we were doing this for a test question, we didn't want to do the whole tree. We know we have 2 things. If neither is damaged, that means the first is damage free and the second is damage free. And again, you could go back up to your little drawing and see what's happening. All right, and then the last one, probability that 1 tire will be damaged. This is the most tricky because as you see here, in this situation we have 1 damaged tire, and in this situation we have 1 damaged tire. So we have 2 ways that this could happen because I could have bought the damaged tire first or second. So technically these are disjoint events, so we would add those 2 probabilities together to get our final probability. Gosh, there we go. But the way I would do this if I was doing this by scratch, again, 2 different things are happening. 1 is damaged, so I'll just go ahead and get that first. If only 1 is damaged, that means the other one must be damage free. However, this is not the only way this could happen, right? I could have switched the places of these. So I'm going to do a multiplier of 2 out in front when I do this actual math. And you'll notice that these gave out the exact same value. That will always happen because all we're basically doing is flip-flopping our numerators. And the associative property or the commutative property tells us it doesn't matter which order we multiply those 2 numerators in. So however many ways you can order them, that's what you're going to multiply by. Notice here with the the 2 damaged tires, there's no way to reorder it. It's the exact same thing. Here we have a different way that we could write this that also gives us an outcome that we care about. So that's why we're going to multiply by this 2. Okay? And again, you could always make the entire tree if that makes you more comfortable. But hopefully after the practice, you won't need it.